now that you're done with the homework, on page 283, I want to talk about it. First, let's look at problem 79, the integral of sine cubed. That we will use strategy 1, okay, on page 275, where you simply you have cubic sine to the third power. So what you're going to do is save 1 sine x, and then what's left, you have sine squared, and you are going to turn that into 1 minus cosine squared, and that will turn the problem into a fairly easy use substitution like this. We have we have sine cubed, so we turn sine squared, part of it, sine squared, into 1 minus cosine squared, and then you will get something like integral of sine x and integral of cosine squared sine x. Okay, being the derivative of cosine is negative sine, then you have the du taken care of, and then you can integrate the whole thing rather quickly. So that's problem number 79. Next, let's look at problem 83. Now 83 you will use the exact same strategy as the previous one. Okay, we have sine to the power fifth and cosine to the power 2. Now in this case, the k in the strategy plan is odd. So what we're going to do is that is the power of sine is odd. Now in that case, we're going to take one, save 1 for the du, and because derivative of cosine is negative sine. So we'll save 1, so we have a sine to the fourth power left, and then we'll convert the sine to the fourth power completely into the cosine. Being that it's the even power, you can convert it into the 1 minus cosine squared. Oops, sorry. Let's see. Okay. So let's see, we have sine to the fourth power, right? Yeah, right here, this line, right? So you have sine to the fourth power, then we convert it to 1 minus cosine squared, then squared again to make sine to the fourth power. And then at that point, you let u equal the cosine x, and then du is minus sine x, and then plug it all in, and it all comes out pretty nicely. Now I want to mention that you notice the answer, once you come out with the answer is not exactly the same as the back of the book. The back of the book converted all the powers back into angles with a lot of numbers in it, which is, we're so not going to do that. Okay, there's no benefit in that, so we're going to stick with this, and we'll call this the right answer. So next, let's do the next problem, problem 85. Now problem 85, you have to do the square root and stuff. That's actually kind of a trick question, okay? Because that's just a direct use substitution. We don't need any strategy for that. And I mean, we're in a section with lots of strategies, so then we have a tendency to get stuck in the rut and look for the strategy every single time instead of looking at the problem and see if there's a quick way out. And in this case, this problem is that derivative of sine is cosine. So if you let u equals the sine of x, then the whole thing pops out, in one line. Basically, you just raise the power by 1, then which becomes 3 halves, and right here, and then divide by 3 halves, and that's your answer. All right, so that's 85. Next, let's look at problem 86. Problem 86 is all right, so the 86 is, then right now the cosine is in odd power. So instead of, we've been doing saving a sine for the du, now we're going to save one of the cosines. So we'll save a cosine for the du, okay, right here. So then we have cosine squared left. And at that point, we simply substitute cosine squared is 1 minus sine squared, and then the whole thing will become, we can put u as sine of x, but it's not really necessary, okay? We can just do this in our heads. So the square root of sine x times cosine x, that's the power 1/2, so you raise it to 3 halves, which is what we just did right here, right? And then the other part, sine 5/2 raised to 7 halves, divided by 7 halves, and that's your answer. Now, being this is an even problem, we don't have the answer at the back of the book, but that's okay. And we are confident that that should be the right answer because the problem is quite short. And so we don't have a lot of ways to mess up. And so let's look at the next problem, which is problem 89. There's a tangent secant situation, which means we're going to use the strategy on page 278. In which, what do we do there? Well, that problem is also fairly direct. What we do is we're going to turn tangent squared into secant minus 1, okay, because tangent squared plus 1 is secant squared. That's the rule. So you beat that around, becomes, and you substitute secant and get rid of the tangent in the equation, and then you end up with 2 secants. So integration, that is integral of secant cubed and then integral of just secant. Now at this point we are not going to calculate the integral of secant cubed because we already did that 3 times so far, okay? And so we're just going to dig the answer out and not worry about how we got it. One answer is on page 280, another one's on page 281, doesn't matter where it is. The point is we are going to take out the answer, and then and the integral of secant x is on page 277. Again, we're not going to figure out why. We're just going to plug that in. So the whole thing is 2 lines, okay? The top line is the secant cubed integral, and the second, and then subtract by the secant integral down here, a little bit down here. So when you do the subtraction, then you get this thing, which is the right answer. Okay, and now, so that problem would have been very, very tough if you didn't know what the integral of secant cube is. But luckily, we've already done that, so so the problem looks a lot better as a result. And then problem 91, we're going to use that, what is that called? Repeat formula or something on page 281. Well, whatever it's called, we're going to plug that in. Okay, just whatever it says, we'll plug it in. And that gives you the first line. And you get down to secant squared. And what's the integral of secant squared? That's just tangent. Okay, remember the derivative of the tangent is secant squared. So that gives you, so the answer came out in 1 line. So that formula on page 281 is pretty neat and handy sometimes. Next, we'll look at problem 93, the integral of cosecant x. Now, the integral of cosecant x is not that simple to do. However, we already did it a little bit earlier, okay? And I mentioned it when we were talking about the integral of secant on page 277. And the trick to doing it is let u equal to cosecant x plus cotangent x, and then you multiply 2 of them. Now, let me show you my notes again. We already talked about this, but I will show it again in case you don't remember it or something. So here it is. Okay, now that's showing pretty good, not too much reflection. What happens is you multiply on the top and the bottom by cosecant x plus cotangent x. Right here, somewhere here. And then you notice that whole thing and then you said, you say u equals the cosecant x plus cotangent x. This is similar to what you do with the secant. See, the secant integration is exactly the same. So, exactly similar. So then du equals to negative cosecant x cotangent x minus cosecant squared x, which just happened to be the exact thing on top of the division line in the integral. So your entire integral gets turned into the integral minus du over u, which comes out very quickly. It's just the natural log, except for the minus. And then you plug the u back in, and then you're good. So that's how we did it before. Problem 95, another trick question, is we've been doing the sine cosine strategy for a long time. Well, here's one that doesn't actually need a strategy. If you pull back a little bit and think about what this is. See, we have sine squared and then we have a cosine. Well, you just the derivative of sine is cosine, so the du is taken care of. If you let u equal to sine a of x, and then you have to adjust for that a there by dividing it out. And then of course there's a 3. So, well, in any case, you just integrate that thing, right? And then it's raised to the 3rd power divided by 3 right here. And then, and of course, you have to take care of the a. So you have to divide by a, because when you do the chain rule in this, the ax will produce an extra a. So you divide it out to take care of that. And then that's the answer. So next, let's look at problem number 27. The integral of sine squared x. Now, how are we going to go about that? The trick in this thing is use that trig identity, the half angle formula, where you knock out the power. See, by using the half angle formula, like right here, see, you have, you have the sine squared x, it just becomes just cosine of 2x, but no power, plus some number, which is okay. And so then once you get rid of the power, then you're just integrating regular old cosine, which comes out very quickly. Okay, and that happened to be 1 pi over 2. Anyway, so that's pi over 2, which is fine. Well, that's because we have to do the evaluation. This is the definite integral, so you have to plug in some numbers, which is okay, right? It's a very simple plugging in. Problem 101, that's even a sillier question, but I assigned it just for the laughs. Okay, now how funny is that? They ask you, what is sine squared plus cosine squared integral? Well, sine squared plus cosine squared is 1, right? You integrate 1, that's x, and that's your answer. And so that's just to be funny. And next, let's look at problem 103. We have integral of cosine x and then sine x, and we're integrating from 0 to 2 pi. Okay, so then we follow the rules. So problem 103, we're supposed to do cosine x and then sine 2x. So that you have two different, there's x and then 2x. So you follow the rule on page 276, where you have, when you sine ax cosine bx equal to the bunch of stuff added together and stuff like that. So you plug it into one of the formulas in there, and then you end up with, in this case, then a will be in the formula will be equal to 2, b in the formula will be equal to 1. Then you end up with something like this, okay, which is just the sine power done twice. So the integration comes right away. It's just the cosine with a negative, and you take care of, being that it's sine 3x up here, you take care of that by dividing by 3, and then evaluating it from 0 to 2 pi, and your answer is 0. Now, why is the answer 0? This part isn't necessary, but I plotted it out just for interest's sake. The reason is because the graph of this thing, I plotted on the computer, but I'll show you here my own hand drawing. Is well, this doesn't look very symmetrical, but it is. Okay, they're identical. That is, the thing looks like this for a while, and then come down and look like this. The bottom part is identical to this top part, and therefore the two areas cancel each other out. And that's not necessary for this doing this problem. I just thought it's neat to mention. Next, let's look at problem 109, where we're doing cosine cube x over square root of sine x. But this is a definite integral from pi over 6 to pi over 3, integrating, which is fine. Well, the trick we're going to pull is, being that cosine is an odd power, we'll take one out. That way it becomes an even power. And then we replace it with cosine squared with 1 minus sine squared. So then everything will be, anyway, and then everything will look much better. So then we have, see this situation, problem right here, 109. We have, and once you have replaced cosine squared, part of this, the cosine cubed, with 1 minus sine squared, then the rest is just a matter of integrating each one, because the derivative of sine is cosine, so your du is taken care of. So you do raised to the power, divide by the power, but this time you have to evaluate it from pi over 6 to pi over 3, which of course you can plug it into your calculator or something, but that's a lot of bother, because we have sine to the 1/2 power and all that stuff. So I find that the easiest and most convenient way of doing that is to use the Desmos calculator's function, the function calculator. Its link is, I have the link written down, typed in under the homework, so you can try using this. What you do is you type in f of x, type all that stuff in, okay, exactly as is. And the decimal calculator, you have to type sign parentheses x, otherwise it doesn't work. And also the raising the power is just push let's see, shift 6. Okay, so then, but anyway, you figure out how to type all that stuff in exactly as is, and then look at the bottom part, and then you can sorry, what is that? I'm not sure, maybe I'm too close to the camera. I'll make it a little bigger, that might be better. All right, so anyway, why is this doing that? All right, so then let's see, we have so now we don't have to look at it too close. Now we have, once you type in the function, and it's much easier to type it on the computer than your TI-84 or whatever it is you're using, then we have what on the bottom, you just plug in the pi over 3, they have a chart already, and then pi over 6, and then the numbers will come out immediately. And then you can, and then what I did is copy and paste those two numbers on the bottom, where on the bottom they allow you to continue to use the calculator. So I copy and pasted pi over 3 and pi over 6 on the bottom and did it, plus the subtraction sign, and the answer came out right away. See down there? And I feel that that might be a better way of doing this. You might even figure out a faster way to use this function calculator. I just started using it, so I'm not 100% familiar yet, but I just want to clue you in that that this can be done if you have access to that calculator that I have the link of. If not, then you have to use the scientific calculator or something and do it the old-fashioned way, which is still okay. But I try to get out of grunt work if I can help it. So next, let's look at problem 111. Problem 111 is 1 minus cosine 2x. The trick to doing that, and you're under the square root and stuff, but the trick to doing that is actually, right. Well, anyway, so this is taking the square root, but we are only worried about values from 0 to pi over 2, during which the cosine value is, let me think about this. I'm worried about something becoming negative. Let me think. Okay, I just remembered that from 0 to pi over 2 sine is positive, so we don't have to think too hard. So keep continuing what I was saying. Problem number 111. We have 1 minus cosine 2x. We'll replace that by the half angle formula as just sine squared x. So then we're taking, and then, but don't forget the 2. See, I messed up on the 2. That's why the first time I tried it, I did come out with the wrong answer. And then I realized that I put the 2 in the wrong place. There should be a square root of 2 multiplying sine x. I mean the square root of sine squared x up here. I'm missing here, there should be a multiple of multiplied by square root of 2, which I have written down here eventually. But anyway, so the idea is that we take the square root of sine squared, which is just sine of x. We actually need to write down the absolute value as well, because when you take the square root of something, you only accept the positive value. However, in this case, we're doing sine from 0 to pi over 2, which sine is positive the whole time, so we can ignore the absolute value. It's not necessary. And so therefore we will continue and say that the integral sine is some negative cosine, and don't forget the square root of 2 there. And once you get that, then you get the right answer over here. Oops, the other side over here. So the only hard part of this problem is that is that I messed up the 2. So but other than that's why the problem's kind of scratched up. But once you figure that out, then the answer is quite straightforward. And the next thing is problem 113, which is again we are doing cosine squared minus sine squared, which is quite hard to do until you realize that that is just cosine 2x. I mean, look at this, right? It's just cosine 2x. And once you plug in cosine 2x, then the whole thing is a piece of cake. You just, plug in the numbers and then come up with the answer. And that should be correct. Yep, I checked and the answer is correct. However, in your book, the answer, they type it in as 1.0, probably because they did this on the integral calculator and never bothered. In reality, it's not 1.0. Okay, why is it 1.0? There's no significant number required. It's exactly 1. It's not just 1.0. So 1 is plenty good enough. And then is this the last problem? Oh, that's the last problem. So I guess that's about it. And so tomorrow, these homework are fairly short, so I haven't been doing it on the board. But tomorrow's homework, I will be definitely doing it on the board, because that is not going to run so smoothly. So let's so tomorrow I'll see you for the next section.